assume that Sean can count correctly. So, here's our results. What is the average of this? And I'm not going to ask you... I'm not going to ask you to calculate this one, this times this plus this times this, because it's just too tedious. And this is what Excel was invented for. But if you were a waiter and you had to carry this tray of cookies, and this was a tray of cookies, right? And it's got the 6 cookie, the 7 cookie, the 8 cookie, the 9 cookie, and so forth. And you had to put your hand, or better yet, a finger under the balance point. Where would you put it?
Probably like 12 or 13.
Tell me where to stop. So here I'm going to put my, you tell me where to stop.
Right about there.
You guys are ish in here? I like that, somewhere about here? Good, very, very nice, very good. Anybody say we should go further?
Yeah.
A little bit further? So, Kelly, tell me where to stop.
About 15.
Okay, so somewhere, you guys are all pretty much in agreement we're somewhere here. Any further, and it's going to be too top-heavy on this side, but any further on this side, it's going to slide down. That would be very, very nice. The actual average, I think I've got, let me just check. I've got it, there it is. Our average is 15.2. Now, let me make sure this is actually adding correctly. D57 times C57. It is actually, because that's the sum. Nope, 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 nope. Hang on. Excel didn't automatically sum it up. 15.1, 15.2, which is damn close to where you guys said it was, yes?
Yeah.
Now here's the interesting thing. That average is actually being skewed a little bit by this 48. Oh, and this is not even showing.
And that's not showing.
Yes, I have to, sorry, hang on one second, guys. This has to change to, I believe, 56 is what it was, right?
59.
59, thank you. 59, thank you for telling me that. And I also have to edit this guy, because he has to go all the way down. I wish Excel was smart enough to do this automatically. Oh no, the cell is 56 though. So hang on, let me just edit this. This should be 56. There we go. That's what your graph actually is. So now, Katie, I see you're 56 way out there. Or you're 59 way out there, excuse me. So this would also be why you guys might not, you guys call the average a little bit about 1 or 2 in from where Excel called it. That's because you couldn't see that extreme tail out there. Now that you see the extreme tail, it makes sense you have to move a little bit further over to catch that tail, yes? So you guys have a nice intuitive feeling as to where the average has to be just by looking at where the results are. Now what I want to do next is compare to the theoretical. There is actually a mathematical answer to this. Check this out, okay? Now this might be a little hard to see. Here are the results that we got in pink right in front. It is pink see-through blocks. That's the same graph that you guys got right here. Let me shrink down so you can see it. See that graph right there? That's that graph in pink right there.
Fancy.
It's super fancy. Can you see? Let me switch the lights up because the lights I think are in the wrong.
That's better.
Is that better? That's a little better, yeah?
Oh, yeah.
The green behind the pink are the theoretical results that should happen. You can actually calculate the theoretical results of taking 2 flips to get, or 2 rolls to get a repeat, or 3 rolls to get a repeat, or 4 rolls to get a repeat, and so forth and so on and so forth and so on. We're going to start developing those tools starting on Wednesday when we actually start formally analyzing probabilities more. How close does our graph look to the theoretical graph? It looks damn close. Now check it out. Here's how I did it. Here's how I did it. I'm going to show you over here. It's kind of hidden behind the graph. Here are the probabilities of getting a repeat within a certain number of trials. For example, I've told you that there is a 1 in 6 chance of getting a repeat on the second roll. Now think about why that has to be. This maybe will make sense to you right now. Roll the first die. What do you get?
1.
Sure. Say it's a 1, or a 2, or a 3, or a 5, or a 6, or a... That's it. That's right. That's it. Or a 4. I forgot one. Or a 4. Now, what's the chance the next roll matches the first roll?
1 in 6.
1 in 6. Boom. That makes sense, doesn't it? I mean, hopefully that makes perfect sense. Yes. So the first roll is irrelevant. You roll whatever you roll first. The next roll is the one that matters. If it has to match the first one, which means it has to match the first one, yes, then it has to be a 1 in 6 chance. That's how you figure out that. Here's where it gets interesting. Suppose it takes 3. This means that you roll the first die and anything happens, yes? Anything happens. So there's a 100% chance of that happening. Now roll the next die. What can't happen on the next die? It can't be the same as the first one. How often does that happen? 5 out of 6 times, yes? So the chance of that happening is 5 out of 6. Does that make sense? 5 out of 6, yes?
And why can't it be?
Because we want to have 3 rolls until we see a repeat.
Oh.
If we got a match on the second one, we'd be in the first category. No, don't be sorry, it's a great question. Yeah?
I just.
Yeah, so don't you worry about it. And I'm actually skipping ahead to next week, if it's okay, just a little bit, to kind of show you where these numbers are coming from. So there's a 5 and 6 chance, which is 83% chance of that happening. Now the next roll has to do what?
Get the repeat.
On what? Who's it have to repeat, Deb? I love this. Or either one of them, yeah? It's either got to match the first one that you rolled or the second one that you rolled, which happens 1 in 3 times, right? Every time you roll a die, if you've already rolled, say, a 1 or a 2, you then have to roll that 1 or 2 again. Deb, I love what you're doing. You're thinking about it right now. You're imagining that die in your hand. You're good. Visualize it. So give me some numbers. What's the first number that you roll? Make it up. 1. Good. Next roll is going to be a 3. Now, what's the third roll have to be? Or a 3, which happens 1 in 3 times. 1/3 of the time, right? Of the 6 outcomes, 2 of them is 1/3. 1/3 times 5/6 ends up being your roughly 28%. Boom. There you go. Does that make sense? I'm getting a little bit ahead of ourselves here, but that's how you calculate the theoretical probabilities. That's how you would go that way all the way down. Notice these match beautifully. You have the same probability of rolling 3 as you do of rolling 4. Now look at our results. That's what we got. Hang on a second. No, we didn't. Wait a minute. Time out, time out. Shoot. This should be calling.
52.
Oh, this is theoretical. I'm sorry. This is, yeah, sorry. This is the theoretical.
Yes.
So these results over here are actually our results. Now we got, hang on, we got 107 and 100, which is damn close to the 104 it should be. That's the point. If you look at the graphs, it looks almost exactly as it should look. Yeah, it looks almost exactly as it should look. That's why when the math is very hard to compute, data analysis will get you the exact answer that you need without having to do the math. So what I was just describing to you guys, and I love the fact, Deb, as soon as I started talking about it, your eyes went up and you started thinking about the outcomes. I love that. It gets extraordinarily tricky as you work yourself down the line, though, to figure out, okay, what am I multiplying by? Is it a 5/6? Is it a 3/4? Is it this? Is it this? Is it this? In the time it takes you to work all that math out, you can collect a bunch of random trials, plot the results, and you see the point? You get essentially the same average. The true average, 3.766 and some change. Our average was 3.8. I mean, hell, it's almost exactly the same, yeah? Pretty awesome. Now, I am going to have to do some fixing on the next sheet, which is the theoretical for the until we saw all the faces. Remember how I had to add those pieces for Katie's 59? Let me turn this off real quick. Give me a couple.